Hello my friends, and welcome again to my video channel. Today we will continue our work on the musical fidelity amplifier A100-X with a very interesting design, and I can promise you more interesting things are ahead. So let's start. This is our test setup. I've installed 50% of the cover to increase the cooling, to improve it a little bit. There's no thermal grease between the heatsink and the cover, but the screws are very tight with a wrench. Here we have the dummy load, 4 ohms, 100 watt, 2 times for the 2 channels. The scope is connected in parallel to the output. 5 volt per division is the setting. Here we can read the RMS value per period. I was looking for an option in the mathematical functions to calculate the output power. I didn't find it. Maybe I'm not clever enough for it. The manual is very thick, answers every question, but the question what I have is not answered by the manual, so I will do it with my calculator. I have the RMS voltage output, I know it's 4 ohms. The rest is a little bit a calculation. Shouldn't be too easy. It is specified to 2 times 50 watt. So 50 watt into 4 ohms, this means an RMS voltage of 14 volt. 14 volt squared is 200. 200 divided by 4 is 50. So we expect 14 volt RMS to have good output power of 50 watt. I will increase the line voltage now, and then we will see what happens. By the way, here's a generator set to 1000 Hertz. Input is auxiliary input. Both inputs are parallel. I have an adapter here to connect it in parallel to the auxiliary input. Now we can see what happens. Now I increase the output voltage or power with the pot, and you see something happens in one channel, but then it's stable again. It's clipping, now it's stable again. And here we get a crossover distortion, high output power. In both channels, as I see. One channel makes trouble, I'm sure it's a pot. Yes, it should be the pot. But with higher output levels, we have an increasing crossover distortion. It's 7 volt RMS. I don't understand why. The pot is a catastrophe, and the circuit, the schematic also. We will have a look at the schematic now to see why it is jumping up with a dirty pot. And this goes over. Now we come to the clipping. Yes. It is 10 volt RMS. 25 watts, not 50. But why do we have these jumps? Okay, still cool. Let's have a look at the schematic. Here we have the schematic. The point of interest is this section, the preamp section with the pot. And what do we see here? The volume pot. It's in the negative feedback. That's incoming signal from the selector, tape and so on. And the amplification of this op-amp is determined by the feedback. More feedback means less amplification, and less feedback means more amplification. It's a negative input here, negative feedback. And when we have here a contact problem, then the feedback jumps up. The feedback is going down to zero, nearly no feedback. only the complete resistor is in, and this means increasing gain. A bad contact here on the wiper means the gain increases. And that's what we have seen in one channel, that the pot is obviously dirty. I hope it's not damaged. It's only dirty, I can clean it. This means increasing output up to maximum. We have seen sometimes the amplitude jump to the maximum output, possible output. This may kill the loudspeaker, or maybe also your ears, or both. First a big bang in the loudspeaker and then a big bang in your ear. I've never seen such a design where the volume pot is in the feedback loop, and with a bad contact the volume would go up nearly to, not infinite. We have here a 50k log pot, but in general we only need a very, very low gain, so we have here a low resistance in the range of, we have a 4.7k, yes, 4k7, so we have here only some 100 ohms or so, maybe 1 kilo ohm, and suddenly it would jump up to a 50 kilo ohm. You can imagine what happens here in the amplifier. Oh no, well, this pot has to be cleaned, and I will take it out. The pot is disassembled. The toughest job was to remove this securing from this axis here, this squeezed on. I think I have it a little bit damaged. The rest is easy. The main problem, as I think, is a contact here between this ring here, which is a wiper, and this counter contact, whether this resistance layer is bad, we will see. Do not use a contact cleaner for this layer, it may be damaged. Use a special fader cleaner. I will use the Oxid what is this, F5 or so. Yes. Such a thing like this one. Not a contact cleaner. Well, I will do it and show you the result. Only for this contact here, by the way. For this contact I will use a contact cleaner. Of course it's metal. The counter contact here is also metal. This can be made with a normal contact cleaner. Pot is cleaned. We reinstall it and resolder it. And now we have you can see here 5 volt per division. Clean signal. One channel, the blue channel, has a little bit more amplitude than the yellow channel. Blue is channel 2. That's a what is it? It's a white channel. But there is no balance setting. This cannot be balanced. But we have some sound. Well, that's okay. Pot is clean now. And I think we can now focus on the next topic. The Bode plot is prepared. These are the two output channels, left and right. I only can write one Bode plot for now. I start with the left channel and then later I switch to the right channel. This is the third input which is used to monitor the generator output, and it's necessary for the Bode plot. And then we can start. It is set between 10 Hz and 30 kHz. Forget the waves in the background, it's just for reference. We have a gain of 17 dB. Okay, it depends upon the setting of the pot, of the volume pot. The phase error is 22, it's going down to 0. When starting with 10 Hz we have of course on phase error, and then we can let it run. We see we have a flat gain of 18 dB. In this case it says nothing, it only tells us something about the setting of the pot, of the volume pot. and up to 30 kilohertz. Okay, here it starts going down, but we have a gain of 17.8 dB. And now I change to the other channel. This is channel 2. Oh, come on. And then let's start the Bode again. 18.4 dB. So that's what we have seen. One channel is a little bit more amplifying than the other one. There's a short dip in it. Don't know why. But they look similar. A little bit more gain. We have a constant gain of 18.7 dB, a little bit more, but that's not critical. And the phase response is also 0 degree, rather linear over the whole range. Now let's check the phono preamp. This stage here, there's a switch MC. Meanwhile, I have learned that means moving magnet and moving coil switch. And in the position moving coil, the switch is closed and this capacitor is switched in the circuit, so the gain of this preamp is increased. It's a PNP transistor, and in the emitter part we have 56 ohms, and the parallel switched 1K and 3.3K. So when the switch is open, we have here approximately for AC 700 ohms, and in series with the 56 ohms. And when this switch is in, then this is bypassed for AF, and we have only the 56 ohms in series in the emitter, so the gain is increased approximately by factor 10 or factor 12 or so. And here we have a compensation, frequency compensation for the magnetic system, but this is constant and it is not switched. There are two RC time constants, and we will see it in the Bode plot that there is something for higher frequencies, that the gain is reduced for high frequencies, because a magnetic system generates more voltage when it moves faster in the kilohertz range, then the induced voltage is higher than in the range of some 100 hertz. Well, let's do the Bode plot for this input here. And input selector is of course in the position tape or phono, sorry, phono, not tape, phono, it's not stated here, it's phono. Now we have the Bode plot for the left channel, moving magnet setting. The yellow one is the output in the amplifier, and the purple one is the input signal. Here we have lower frequencies from 10 Hz up to 50 Hz. Increase in the gain, of course, the coupling capacitors are limiting the lower frequencies, but for higher frequencies we have a considerable drop in the gain. The phase, of course, has a big variation, but that's not so important. The amplitude is decisive. Again, we are running from 10 Hz to 30 kilohertz. Okay, and now we go to the other channel, channel 2 for the Bode. We had here maximum 46 dB. Now let's see what we have in the right channel. (44 dB), 46. So there's a little bit of hump, don't know why. In the range of 50 Hz, maybe there is some coupling, not sure. Could be a ground loop, unwanted ground loop. but we have the same maximum gain, 46 dB. Okay, now I switch to moving coil. Is it right? Yes, moving coil. Do the same measurement. We have a 46 dB. I start with the same right channel just to see what's going on with more sensitivity. The signal is overdriven. This is not okay. Not okay. No, no, no. Here we have the Bode plot running now in the moving coil setting. It's a little bit tricky because it's very sensitive, the input. I have to attenuate it. Maximum gain is 40 dB. Depends upon the setting of the AF volume pot, of course. But we see also the drop at higher frequencies. Let's see, channel 1, left channel. And then we compare it with the right channel. And see whether we also have 40 dB maximum. And we can start. The purple, the blue one is the channel 2, the yellow one can be ignored. It's overdriven with 22 millivolt setting. (41). You see there is an additional frequency. I assume it's a ground loop anywhere in my setup here. I have a scope, I have the amplifier, and we are measuring in the range of millivolts. So maximum gain is 41 dB. I had a problem with a ground tube or so. I'm doing the measurement for moving magnet and moving coil in a different way. I simply feed in the signal. It's 60 Hertz, where we have the maximum sensitivity. Moving magnet, both channels, and now we have moving coil, both channels. I simply switch over, and we see we have again a little bit more amplitude on the right channel as we had before, and the other inputs. Well, that's it. The other inputs are also okay. Now I can continue and remount the whole amplifier. And now the final test. The amplifier is completely reassembled with a lot of thermal compound on the heatsink here. All screws are fixed. Switch is operating now. We have to check whether the output impedance is 4 ohm or 8 ohm. I'm not quite sure. At the moment I think it's 8 ohm, the nominal output impedance, but there is no sticker on it, no label. I don't know what is the nominal impedance. What's the frequency range? What's the line voltage? I think it's 220 volt as it was earlier, but today we have 230 volt. There's no label. Maybe there was a label and it was lost by generating the heat. It's running for about 15 minutes. It's getting a little bit warm. Up to now it's okay. I have a load installed 4 ohms 2 times. Signal generator 1 kilohertz. At 4 ohm load, I assume it is specified 100 watt. 100 means 100 watt. It is 2 times 50 watt. 50 watt per channel. With 4 ohm it should be 20 volt peak. And when we have a look at the scope, we are connected here 10 volt per division. We do not reach it. We have saturation earlier in the positive range, and we have here crossover problem. We have here crossover problem in both channels more or less, but we do not reach 50 watt in a 4 ohm system. So I will swap it to 8 ohm and we can see whether it's a good system for 8 ohms. My dummy load is only good for 2 times 4 ohm or 1 time 8 ohm. Again 4 ohm on the left channel only, and we see we have a limit at more or less 20 volt peak, but with heavy distortions. Now I go to 8 ohm system, I add the 2 impedances in series, make a short. Oops. Now we have 4 and 4, it's 8 ohms, and in 8 ohms we should have 28 volt peak. That's a 30 volt peak, and I think it's better, but still small crossover distortion. But in general we have in this 8 ohm system 50 ohms when we don't talk in detail about this crossover problem. And now I go to the right channel. Okay, more or less the same. So I think this is an 8 ohm system, not a 4 ohm system, and I will do the distortion measurement now in the 8 ohm system and see what the result is at lower output levels. For example, half a watt or 1 watt, which is the typical output power for a living room, and then with a power of 30 or 40 watts. Now let's start the THD measurement with 0.5 watt, 500 milliwatt into 8 ohms. That's 2 volt RMS on the left channel. That's the output, and we go to the THD measurement. Set the level to was too much. Okay, full scale 100%. And then we go to distortion. We have 1% full scale, 0.04. Looks good. And now we go to 1 watt. We have 0.03, nearly the same value as before. 0.03%. So in low power output we have a very good THD. And now let's go to 30 watt outputs. And we can see already a little bit the distortion, crossover distortion at 15 watt. This will give a bad result. And the THD, we'll set the full scale. Now we go to distortion measurement. This is 1% full scale. We have 0.9% at 30 watt. Not so nice. Maybe we should go, just for curiosity, a little bit down in the output power. So we have 10 volt RMS. That's approximately 12 watt. Let's set the level to 100%. Distortion measurement. 1% full scale. Okay, we are again in the range of 0.1% at 12 watt. Well, I checked the right channel also, but I think it will have the same results. So we can say in low output power, 10 volt RMS, we have a very good THD, less than 0.1%. In the higher ranges, due to the crossover distortion, we have, of course, a bad THD. And now we check the right channel. The measurement of left and right channel made no big difference. At 0.5 watt, 500 milliwatt, we have a distortion, total harmonic distortion of 0.04%, 0.03 left and right channel. Same as with 1 watt, 0.03% left and right channel. At 12 watt we have 0.1%. The other channel is a little bit better 0.05%. At 30 watt we have an increasing THD of 0.9% or 1.2%. We have seen there's still a crossover distortion, and at 50 watt I didn't measure it, makes no sense. Well, job is done. My friend only asked me to bring this amplifier back to life so I can hear a little bit music. He's not a hi-fi enthusiast or so. It works. I have connected a sounds good. The boxes are a catastrophe. Well, some words about this amplifier. There is no balance control, not inside, not outside. There's no tone control, no bass, no treble setting, nothing. Where should it be? Where should it be done? In the preamplifier, but we have several inputs here, so each input would need an own equalizer, not a solution. And most important, there is no internal protection circuit. What is a protection circuit good for? Well, it protects the speakers against being deleted if there is a high DC output level. If one transistor dies, output transistor dies, or one of the driver transistor dies and generates a high DC output voltage, then the speakers will be roasted, the coils in the speaker, especially the bass speaker. This protection circuit is not present. There is no fuse on the secondary side. The only fuse is on the primary side, on 230 volt AC. It's a slow blow fuse. And you can imagine what is faster, the coil in the speaker or the fuse on the primary, the slow blow. The coil in the speaker is faster. So this amplifier, I say carefully, it wouldn't be my first choice. Okay, please don't ask me what my first choice is. I'm not an hi-fi enthusiast. But this, no. Definitely no. It's generating heat. 60 degree. I have an idea what I can do with it. It's an option to keep my coffee warm. And here we have the list of casualties. These are the big 4 electrolytics from the power supply. We have seen they are obviously okay, but the rated voltage is only 35 volt DC, and we have a supply voltage close to 35 volt, so I think it was a good idea to replace them by 40 volt types. 4 output transistors, 3 were bad, the switch was broken. Here we have the Zener diodes are replaced by bigger ones, they got hot. These are the 4 resistors, 4.7 megohm. I increased to 5.6 to reduce a little bit the bias current. These are the 4 collector resistors, 0.22 ohms. They were a little bit burned. And all electrolytics, all other electrolytics. This one, for example, when we look at it, is heavily decolorized. I will measure it, and the other one, which was in the heatsink, I don't know which it was, maybe this one. I will measure some and look whether they are still okay or not. This one should have 1000 microfarad, it only has 450 at 120 Hertz. The quality is also very bad. The dissipation factor is 1.5, there should be 0. something. And now I measure this totally decolorized. Might be, by the way, the tube is shrinked. Here we have a capacitor should have, what is it? Is it 10 microfarad? Yes, I think, yes, 10 microfarad. Should have 10 and has 6.5. It's heavily roasted. This one should have 470. Oh, 480, that's okay. Yeah, good one. Okay, don't check every capacitor just to show. Should also have 470, yes. These are good ones. This one is also a little bit decolorized on one side. Let's check it. Should have 10 microfarad. There's nothing. Dead. Completely dead. And so on and so on. It was a good idea to swap them all. And now we are at the end of this project with this amplifier. You've seen there are some internal problems, some design flaws, and other things which shouldn't be in such an amplifier. They are still sold in this modification as I've seen on the website of the manufacturer. It's up to you whether you buy it or not. I have a clear opinion about it. Well, that's it. Stay healthy, stay tuned. See you on this channel.